So just a small addition to what I was saying about these complex numbers. In many cases in acoustics, you would like actually to fabricate the signal which is this complex signal. In fact, this is useful in electromagnetics, in radar, for example. One actually works with the analytic signal. One has a real signal, and it's useful to actually fabricate the complex signal, which is x plus I, y. So how do you, the condition for that is that x has to be at a constant frequency or has a small bandwidth. So suppose you have a signal x of t, and you want to get this analytic signal x plus I, y. How do you do that? Well, there is a simple tool which is called the Hilbert transform. The Hilbert transform takes a signal x of t and produces y of t, which is in quadrature with x. So here you get y of t, and then what you do, you multiply y by I, and you make the sum. So you take this, and you get z. And so you have, in your computer, you can have the complex signal as well. Suppose you have the real signal, you fabricate the complex signal just by this Hilbert transform. Okay, so let's continue now this traveling in acoustics. And the next topic is, what do you do now when you have more complicated systems? Up to now, we looked at systems which were at constant area, one-dimensional. What do you do when you have a change in area here, or when you have a change in the density or speed of sound here? Basically, what you do is that at the point where you have the change, you have to write jump conditions. So how do you handle such a situation here? For example, you write the pressure in this section here. So now, why do we look at something like that? Because many practical systems are like that. You have systems which are connected cavities and volumes, and then you have pipes and channels, and you would like to have a simple way to analyze these systems. Of course, the other way is to just do Helmholtz calculations using the complex geometry, using finite elements. But still, it's useful in many cases to understand systems of that kind. So you write here a wave which goes like that, and the blue wave which goes in the negative x direction. AG, BG, it's useful to actually take the position xj, the beginning of this channel, as the reference here. And then you have the velocity which corresponds to that, which is written here. And now you have to write conditions, matching conditions at the change in section. The two matching conditions for acoustics are as follows. The pressure has to be continuous. And the other condition is that the volumetric flow rate has to be continuous across the boundary. So basically, these are the two conditions. Sj times Vj, the acoustic velocity, is equal to Sj plus 1 times Vj plus 1. And then you take these expressions, and you write these two conditions, and you see you have what happens on the J channel connected to the J plus 1 channel here, and you have these expressions for the velocities. And you see that this is like a matrix, so you can extract Aj plus 1 and Bj plus 1 from these two expressions here. It takes the form of a matrix, and you see these are the expressions of Aj plus 1 and Bj plus 1. So you can give what happens in the J's channel with respect to what happens in the J plus 1 with what happens in the J's channel. So that, and the quantities which are coming in here are these ratios of impedances multiplied by the areas. You see this ratio of areas. You can work that out by yourselves. The principle is simple. There is nothing complicated here, except that when you have to write it, it's boring. You know, you have to, and especially if it's on a computer, you have to put all the symbols and so on. But yeah. So this is how you handle these changes in sections, and that's very useful in practice. In the notes, you will see I'm not going to run in those because it would take time, and I don't have that time here. So, but if you want to look at waves which are coming out from a source, which is here, it's this Helmholtz equation, and you assume that it's radial symmetry. This is harmonic waves, spherical waves. Actually, these are the waves that I'm emitting at this point. You have spherical waves. They diminish like 1 over r as you go. It's not quite true here because there are walls, so there is reverberation by the walls. But basically, this is what copes with this emission of waves. And what you find out is that this expression here can be written like that, so that the pressure multiplied by the distance satisfies this very simple differential equation. You know the solutions, and you see they decrease like 1 over r. There is this exponential IKR, and you can write waves traveling outwards, they are like that. Waves traveling inwards, and they are like this. And then you have one problem which you can do by yourselves if you wish, is the pulsating sphere. It's the simplest loudspeaker. Let's assume that you have a loudspeaker with an acceleration W dot. And your loudspeaker is a sphere. Why a sphere? Because this is the simple case. The other loudspeakers are more complicated. So this one is simple. You have a wave which travels outwards, and you want to match the vibration of the speaker to the sound field. So you don't know A. It's a simple matter. You use the momentum equation. You have the acceleration here. You write down that the gradient in pressure has to be like that. And very rapidly you get to this equation here, which gives you the amplitude of your sound field. And this is how it looks. And you have a wave which travels outwards. It diminishes like 1 over r. And basically the loudspeaker, the amplitude that it gives to the pressure field is ρ0 times W dot times A square. So for example, if you have a small loudspeaker, A square is very small, and you cannot have a very large pressure field. It's impossible. It's too small. So to get a large pressure field in a place, you need a big area. So that's why you have this, when you have a rock concert, you have big woofers. They have to be very, very large, and as a consequence, you inundate everybody with sound. So basically, this is what it tells. You have to have an acceleration here, and you have to have area here. And in fact, this is volume acceleration. It's this which comes into the picture. If you want a large pressure field, this is what you get. You multiply the acceleration by A square. All right. So now I ran a little bit in these few slides, but you can actually work them out if you want. You will learn about radiation in 3 dimensions. So let's now go to the energy principles, because you know that we are always interested in fields, but we are also interested in the energy balance. And is it possible to write an energy balance? So this can be done here in acoustics. And we begin with the 2 equations, the linearized equations, 1 over c square dp1 by dt plus ρ0 divergence of v1 is equal to 0, and the other one is rho 0 dV1 by dt plus gradient of P1 is equal to 0. And then we multiply this one by P1, and divide by rho 0. And we multiply this one in the scalar way by V1. So what happens here? We have, and we add these two equations. So what comes out? D by dt of 1/2 rho 0 c square, this is constant, I can put it here, P1 square, plus rho 0 can be also placed inside here, V1 square over 2, like that, plus, and now we have two terms, P1 divergence of V1 plus V1 gradient of P1 is equal to 0. And these two terms can be assembled into a single one, which is divergence of PV1. So now the balance that we got here is as follows. We can write it like that. D by dt of E plus divergence of F is equal to 0. F is a flux here. E is equal to 1/2 of P1 square divided by rho 0 c square plus 1/2 of rho 0 V1 square. And F, so this is an energy density. We will see that in a minute. F is equal to P1, the pressure fluctuation, V1, and this is an energy flux. So energy density and this is energy flux. So why is it an energy density? You see, this is like mass times velocity square divided by volume. So it's really something like mv square divided by a volume. It's a density. You can also do that more formally by saying this is m L over 3 times L2 T minus 2. So it makes ML2 T minus 2. So this is typically energy divided by L3. So it's energy density. It's the acoustic energy density. And the energy flux, you look at that. This is pressure, M, L minus 1, T minus 2, multiplied by velocity, LT minus 1. And so this gives M, T minus 3. So this is like M, L2, T minus 3 divided by L2. So it's like power divided by surface. So it's a flux. It's an energy flux. It's the power that goes through a surface. So this is our balance of acoustic energy. You see, this is what comes out here. It is very close to the Poynting theorem in electromagnetics. Of course, the quantities are not the same, but basically the demonstration is very, very close to what you find in electromagnetics. And what we will see is that when we have a reactive flow, this is changed. And of course, the chemical reaction, the fluctuations in heat release will produce a source inside this, balance. Yeah, let me go back to this, to the value, the level of pressure corresponding to the decibels. Here you have the scale, and in fact you have the definition of the decibels. You see, now a decibel is a logarithmic quantity. You speak about decibels also for the gain of an amplifier. There is nothing acoustics in that, it's just the gain. But here we use that for acoustics. So basically what we have is the pressure, root mean square here, divided by a reference pressure. The reference pressure is very, very small, 2 × 10⁻⁵ pascals. And what you can see here is that 20 decibels is this very low level of pascals. 100 decibels is 2. 120 is 20 pascals. 140, 200. 160, 2,000. 180, 20,000. And we've been able, in a box, to reach 210 or 20 decibels. We had acoustic waves produced in a box at a level as high as 20 bars peak to peak. So 20 bars at a kilohertz, not at zero frequency, at a kilohertz. So that's perhaps a world record. I don't know. Not quite, because the rockets produce even higher levels. Yes?
What's the smallest decibel range you can hear?
Oh, the smallest, apparently babies can hear something like that around here. Yeah, but you lose that as you grow older, and then and especially if you use devices which blasters, things. This will cost you a lot of decibels. For example, you go into a big rock concert. When you go out, you don't hear anymore. If you forgot your earplugs at home, you're done. It takes a while before you get back into listening properly. So this is already the pain, the level of pain. So it's not anymore a pleasure, it's a pain afterwards. And the typical oscillations in practical systems can reach 160 decibels, levels of that kind, or even higher for the rocket engine oscillations. Yes?
Can that still be described as linear acoustics?
So it becomes a place where you have nonlinear effects taking place. Yes? Oh. Can one describe that as it's still linear acoustics? And the answer is not really, because you get to very high levels. Nevertheless, nature is forgiving, and you can use linear acoustics at least as a first approximation. But it's still a fraction of the level. Yeah. Yes, definitely. The question is, are there interesting effects introduced by nonlinear acoustics into combustion instability? Well, the first nonlinearity in our field here is combustion itself. But then the acoustics can also be nonlinear, and there is a whole theory of that. Fred Kulik has extensively worked on the coupling of modes, for example, due to the nonlinear acoustics. But as a first, the first level of treatment is to say the acoustics is linear, the nonlinearity is concentrated in combustion. Yeah. There is another level of intensity. This is the intensity level, and it's the intensity divided by a reference intensity. What is the intensity? It's just the flux. When you look at this expression for a monochromatic wave, you get this intensity. So you have a level, the intensity is just this expression here. And what you have here is a reference intensity is 10 to the minus 12 watts per square meter. So it's very small, apparently. And why, you see these two expressions are compatible, because when you look at the intensity for a plane wave at a distance, or a plane wave, it's p squared divided by rho 0 c, and taking rho 0 c is equal to 400 in this atmosphere, you find that for the reference RMS pressure, 210 to the minus 5, you have exactly this reference intensity. So the definitions, these two definitions, give you the same level of decibels, either using the intensity level or the sound level gives you the same answer here. But of course, if the temperature is different, it doesn't work anymore. This is good for room temperature acoustics. All right, so here we've done this one, and now we turn to reactive case. So in this case, what we want to do is now look at these equations, but we have now fluctuations in the heat release. The small change that we are going to look at is to assume that we have now in this balance equation for the entropy, we now have a term on the right-hand side. Previously, we had 0 here. As a consequence, we will have perturbations in entropy. You see, these two equations are not changed, but here we now have an equation where you have a perturbation in the entropy here. And this is due to the fluctuations in heat release. So what is changed by that is the fact that now this expression here has to be differentiated with respect to the density, but also with respect to the entropy. This is the main difference here. You see the heat release is now fluctuating, and so we now have P is equal to P of rho and S. And so dP is P1, will be a function of rho 1 here, or d rho. Let's put it d rho here first, plus a function of S, dP by ds, times ds here. So this is at constant rho, this is at constant S. And so this is P1. The first derivative is just C squared rho 1. And the second one here that we will call alpha. So this is what I call alpha. And this is times S1. What is alpha? Well, it can be directly obtained from P is equal to rho power gamma e to the S over CV. So dP by ds at constant rho is equal to 1 over CV rho gamma e to the S over CV. So this is like P divided by CV. And just to, of course, this is valid for perfect gases. So P is equal to rho RT, and CV is equal to R divided by gamma minus 1. So alpha is equal to gamma minus 1 divided by alpha is equal to gamma minus 1 multiplied by rho t. Is it so? Yeah. Yeah. It's surprising me just like that. Well, I don't know why. Well, anyway, gamma minus 1 times rho t. Okay, so we have an expression for alpha, and so the main change here is this this expression, and we will see now what comes out. So so you see the rho 1. So now the change here is that rho 1, if we want to eliminate rho 1, we have to write rho 1 is equal to P1 minus alpha S1 divided by C squared. It's P1 divided by C squared minus alpha S1 divided by C squared. So, so this will be put into the equation for the density, and this equation is replaced by d by dt of P1 over C squared minus alpha d by dt of S1, and this is divided by C squared, plus rho 0 divergence of V1. So this is the new balance of mass, and you see that d by dt of S1 comes in here, but d by dt of S1 is known. We knew that value from before. You see the d by dt of S1 is Q dot 1 divided by rho 0 T0. Of course, when we calculate this is at rho 0 T0. So, so this equation becomes it's very close to the previous balance equation of mass, but now we have a new term which comes from the equation for the entropy. You see, this gives 1 over C squared dP1 by dt. And then we plus rho 0 divergence of V1 is equal to alpha divided by C squared ds1 by dt. And now ds1 by dt is equal to Q dot 1. So this is the fluctuation in heat release divided by rho 0 T0. And we know that alpha is equal to gamma minus 1 times rho 0 T0. So now this equation becomes 1 over C squared dP1 by dt plus rho 0 divergence of V1 is equal to gamma minus 1 C squared Q dot 1. And the rho 0 T0 disappears. So that's nice, because now we are almost, it's almost like before. Well, here I left it alpha over rho 0 T0 1 over C squared, but basically it's this equation. And we can actually, yeah, we find that. And now we can derive the equation, the wave equation, by combining this with the balance of momentum. The momentum can be written rho 0 dV by dt, dV1 by dt, plus gradient of P1 is equal to 0. So by taking d by dt of the first one, and by taking the divergence of the second one and minus sign, you get here 1 over c square d2p by dt square minus Laplacian of P1. So previously we had 0 on the right-hand side, but now we have gamma minus 1 over c square d by dt of q dot 1. So the effect of the heat release fluctuations is that now we have a source term inside on the right-hand side of the wave equation. This is what we see in this equation in red there. And now there are many things that we can study with that. The first one is to see what happens to a compact flame. If you have, very often these instabilities are such that the wavelength is large compared to the flame dimension. So we designate that as compact flames. So the situation is, again, we take again the equation here, this equation, and we assume that the flame is compact, for example, like that, and we want to see the conditions on the two sides of what happens to conditions on the two sides of the flame. So we take this, we have already seen. So the equation is here. We can write that down by dividing by rho 0. And in many cases, you know, rho 0 c square is gamma p. We've seen that c square is gamma p over rho. And this quantity, the pressure across the flame, is essentially constant. Most of our applications, the pressure variation in the chamber is not very large. The combustion is essentially isobaric. Of course, not in detonations. In detonations, the pressure difference is very large, but for all these turbulent flames that we look at, the pressure is essentially constant. The mean pressure is essentially constant. So we can consider that this is essentially constant across the flame. We have divergence of V1 here and gamma minus 1 over rho 0 c squared. So this quantity here is a constant across the flame. So we integrate that expression on the volume. We integrate this on the volume and this on the volume. We take this out. Let's assume that gamma is constant and this is constant. We take that out because this is a constant. And we assume that the volume here is very small, that it's very, that the flame is in a small volume. And so this will give just the surface here multiplied by the velocity fluctuation on this side minus the surface multiplied by the velocity fluctuation on that side. And here what we have is gamma minus 1 over rho c squared q dot prime. Q dot prime is in fact this quantity integrated over the volume. It's the fluctuation of heat release integrated over the volume which comes in here. So the difference in volume flow rate, you see, across the flame is given by this quantity here. So that's a nice result. It's been used very extensively because many flames can be treated as compact, and so we can relate what happens on the two sides of the flames using that expression here. You see the derivation is just to assume that this volume is very thin, so that term vanishes, while this one is the jump in the volume flow rate. And from that, you see we can write the velocities. Now let's assume that the two areas are the same on the two sides of the flame. So in that case, what we have is that the fluctuation of velocity on the two sides of the flame V prime 2 minus V prime 1 is equal to gamma minus 1 over rho 0 c square times 1 over s. So this s comes from here, and we assume that the two areas were the same, times q prime dot. It's the heat release rate fluctuation. And this is the heat release integrated on the volume. And very often now we've been using this concept of transfer function. That is, let's consider a quantity which depends on omega, which depends on the frequency, and which is equal to the heat release fluctuation divided by the heat release rate, and all of this divided by the velocity fluctuation, and this is the velocity fluctuation on the upstream side divided by the mean velocity here. This is what we designate as the transfer function, the flame transfer function. And so using that expression, we can see that V prime 2 minus V prime 1 is equal to gamma minus 1 over rho 0 c square, 1 over s, and then we can use this transfer function. So we multiply, we place f of omega here, we multiply by q dot bar, and we have V bar in the denominator here. So that does it, and you have V prime 1 here. So this expression here is very useful. In many cases, we can use that. What we see from that is that what really matters is this heat release divided by the area. It's this quantity here. This is what matters. It's this flux of power due to combustion, which will multiply this transfer function here. And what happens here is that the velocity on the downstream side of the flame is related to the velocity on the upstream side plus this quantity here. So, and if we go even a step further, it is possible to write the heat release in terms of the burn gas temperature, the adiabatic flame temperature, multiplied by m dot times Cp, and we have also rho 0 c squared times s times v is equal to m dot, because you have rho 0 s times v, it's m dot, gamma r Tu, and when you write this expression here in terms of these two quantities here, basically Tb over Tu minus 1 comes in. So we arrive to this very simple expression. The velocity on the downstream side of the flame is equal to the velocity on the upstream side plus Tb over Tu minus 1 f of omega times V prime 1. So that's often used especially in the gas turbine, the premixed gas turbine industry. Another point here is what happens to the balance of acoustic energy. And you remember we did that already with 0 here, but now we have this new term, and when we multiply this expression by P1, you have Q dot 1 times P1, which comes in. So here is the acoustic energy density, here's the flux. These are the two quantity, density and flux. And then we have a source term which is equal to P1 times Q dot 1. So this is the Rayleigh source term. You see this will be positive if the pressure and the heat release rate are in phase, and then we expect that this acoustic energy can increase if this term is positive. So the discussion is about the source term here. This source term, if it's positive, it feeds energy into this balance. So we can write an expression of this kind with S is the source term. The source term is given by that expression here. But of course, we neglected here up to now all the damping terms. But we have damping. There is damping in systems. And more or less empirically, we put a damping term here. It's difficult, in fact, to predict damping. Damping is less easy to predict in various systems. In mechanical systems, it's very difficult to get a right value for the damping. It's not easy. And often it's not so well known. Sometimes you can measure damping using resonance curves. I'll show that later. But this is something difficult to have a knowledge of the value of damping, because if the source term is greater than the damping term, then this energy can increase. And if it's less than the damping, it will decrease. So the damping is not so easy to know. It's something less easy to get. Yeah. Coming back again, you see when we take this expression, the expression for the instantaneous balance, and you can integrate that over a period when you have harmonic signals, then you have here the integrated over a period energy, the integrated over a period flux, the source term, which is now integrated over a period, and the damping term, which is also integrated over the period. So if the source term is positive, it tends to increase the acoustic energy density. However, this energy density will grow locally if the source term is greater than the damping term and the acoustic energy flux leaving the volume. So, of course, the other possibility to damp acoustics is to have energy leaving the volume. If you have a nozzle, for example, it has a certain impedance, and there is some energy which is leaving the system through this impedance. If you have an open end, there is a radiation impedance, and this will also radiate some sound away, and so this will produce a term here. So the energy here will only increase if this term is greater than this and greater than that. It's you understand this sort of thing. If you want to see a little more on the use of this equation, you know, this is closely related to the so-called Rayleigh criterion. Rayleigh explained instabilities by saying that if the pressure and fluctuation in heat release are in phase, you have a growth of instability. In fact, it's not quite so. You have a growth if this term is greater than the damping and greater also than these fluxes which escape from the boundaries. So you can look at this paper. We tried actually to measure this balance, to look at the balance in a few systems. And this was initiated by Daniel Durox, and we wrote that. Again, this is what I've just said. If you have this greater than that and that, then you have a growth in the energy. It is possible actually to measure this term. Now, how do you measure the term? You know the heat release. For example, you measure the heat release looking at my God. Let's go, which way? That way?
In a room full of some buttons.